Today, I will talk about some dynamics of at least different kinds of scalar fields. And we will see that their steady states will lead to some athermal states. Now, whether they're athermal states or they're pre-thermal states in the sense that you are calculating this under some approximation. So maybe there are higher order terms which will ultimately lead to thermalization. That is why the talk, it says A or pre. I mean, it's a different, it's a question of exactly how you want to deal with it. Let me start my talk by saying a few things, maybe also tying up with what Joe was trying to do. One way of dealing with non-equilibrium dynamics is well known, which is the Schwinger-Keldysh field theory. It can deal with open dynamics, it can deal with closed dynamics. Of course, once you have interacting systems, you have to make some approximations, as in anything, to make some analytic progress or so on and so forth. Now, what it turns out is that the textbook versions of Schwinger-Keldysh field theory, which you can take out a textbook and open, requires a very specific kind of initial conditions for the whole formalism to go through. More specifically, you have to start from thermal states, and then you can do something. We have been developing some techniques over the last couple of years where we have been asking, can we do basically enhance this scope of Schwinger-Keldysh field theory so that it can treat dynamics starting from some arbitrary initial conditions. I will not take you through the whole process. I will just indicate what the things are that we have done. And if you are interested, we can talk later. But then what we will do is we will start applying this formalism into two different cases. One is a simple open quantum system where I have phonons or basic scalar fields coupled to fermionic baths. And in this case, if you go to one dimension, that is your fermionic bath is 1D, we will find that at low temperatures, the long wavelength modes of phonons do not thermalize. This is not surprising because there are strong energy momentum constraints. And once I draw a few pictures, you will see that this is not a very surprising result at all. It's what you would have expected. What is least expected is when you go to very high temperatures of the bath, where this kind of strong energy momentum constraints are relaxed because you are at high temperature, even then the long wavelength phonon modes do not thermalize. And we will see how this is because of the dressing by the bath and how new kind of modes emerge out of the dressing of the phonon with the fermionic bath, which we call here polarinon modes, and they lead to the non-thermalization at high temperatures in this case. This is work done with my student Mursal in Islam and has been published. And in the later half, I'll try to talk about interacting scalar fields, which have a dipole symmetry, that's the dipole moment conservation. This will be closed system dynamics under a quench. And what we will see, this is work done with Mursalin and Krishnendu, who is in the audience. And we will see that there are certain phases with certain symmetries which are not present in the thermal phase diagram of the model that we will take. But these phases make their appearances when we do quench and look at the steady states. So that's the interesting features. So let me go on and start a little bit, talking a little bit about the initial conditions. Why initial conditions are important, it's probably not useful to tell you guys. All of you know. There are many experiments. I have just taken one, which is the imbalance experiments, where you start from 1, 0, 1, 0 kind of initial condition in an interacting disordered system. And then the imbalance or the initial memory of the initial condition is retained if you have enough disorder in the system, and so on. There are other cases where you might be interested in influence of initial conditions, transient short-time dynamics. Sometimes steady states in absence of thermalization depends on where you start from. There can be multiple steady states, and depending on where you start, you can go there. MBL and quantum scars, where the dynamics are very much dependent on where you start from. Glassy dynamics, quantum computation, etc., etc. The main point, as I was going to tell you, is that you can look at non-equilibrium dynamics of many body systems, by just looking at the evolution of the density matrix. There is a U, rho of 0 is the initial density matrix, and there's a U dagger. You can expand the U and U dagger in a path integral, and this gives you two fields, just like Joe was getting two noises for the two parts, forward and backward evolution. This is not noises, these are quantum fields. So you will get two fields, phi plus and phi minus, and then you can write down a path integral notation, a partition function, and can do whatever you do with usual field theories, except you have two fields at each space-time point. The one thing that the initial condition comes up as is a matrix element of phi plus and phi minus in between these coherent states. This is how your initial condition enters into your path integral. And so what we have been trying to do is there a way to exponentiate this? Because then I can write it as a part of action and do my usual tricks with field theories. Answer is yes, because after all, at least for things which are Fock states, or density matrices which are diagonal in Fock states, this turns out to be a polynomial essentially, and a polynomial can be generated from an exponential by taking enough derivatives. That's basically how the calculations go. So you introduce some sources, raise it to the exponential, and then take a bunch of derivatives and so on. And so this kind of models where you do not use this part that much have been used a lot, steady states of devices, dynamics, where you're saying you're going to a steady state where you don't care about the initial condition and so on. And what we have been doing is that we have been, with my earlier student, Anna Chakrabarty and others, we have been looking at how to extend this to arbitrary initial density matrices. And we managed to do this for Schrodinger theories, bosons and fermions. And with my current student, we have been able to extend this to scalar field theories. So what's the difference here? The equation of motion is first order in time derivative. So you essentially, all the initial condition you need is the fields at initial condition, at the initial point, or the correlation of the fields in the initial time. That will be enough to initial conditions to give you the full theory. Here, of course, the equation of motion is second order in time derivatives. So you will need not only the initial correlation of the fields, but the initial correlation of the time derivative of the fields. They will also come and sit in this. I will not go through all the, yes. It's about field configuration at the initial stage. No, this last part that I'm saying is going to come from the fact that you need initial correlations and so on is a question of initial density matrix, right? But can you write it in terms of the initial correlations? And if you have second order, it's not enough to know initial correlations. It's important that you know the phi dot correlator, for example. It's not enough to know the phi correlator. That's Feynman-Vernon usually works here, where phi correlators are enough. But in principle, yeah, I mean, yeah. So it's not quite Feynman-Vernon here. Okay. So in the end, what you will get out of this whole shenanigan is that you will be able to write down dynamical equations for correlation functions and try to solve them and so on and so forth. So I'm not going to go into the details of how this is derived, but we are going to use this implicitly when I show you the data of how we calculate the dynamics. So I just wanted to give you a little bit of a plug. If you're interested, you can look at these papers for the full scale derivation. But let me go into the interesting things that we find. So the first thing I want to talk about is that if you have phonons which are coupled to a fermionic bath in one dimension, then the phonon modes do not thermalize. Okay, so how do we see this? Let's take a model. We have a bunch of phonons with dispersion omega k square. These are gapless, at sine k. I'm putting it on a lattice so that it is sine k over 2. And the phonon bandwidth is given by some scale omega naught. Fermions are just hopping on a lattice. So there's a fermion bandwidth, epsilon b. Again, these are non-interacting. And then I have a system bath coupling between the phonons and the fermions, which is the standard form, chi dagger chi, coupled with phi, which is the phonon field. And the coupling has a sign QA over 2 because this is the standard deformation potential. I mean, if Q goes to 0, the phonon mode is just a basic translation, and then there's no coupling to the fermions. So the whatever coupling you have, that matrix element will have to go to 0 as Q goes to 0. And so this is a very standard electron phonon type coupling. Now, what do we do with this? The fermion is then put in a bath, which has a temperature T and a chemical potential mu. Now, you will immediately see that the phonons couple to chi dagger K plus Q chi K, which is like coupling it to the particle hole density of states. And you can make the bath spectral, define the bath spectral function, which basically gives you how the bath talks to the phonons. And this is essentially related to the particle hole density of states. So once I do this, what we did was, we are theorists, so we put an initial condition where it is very easy for us to track whether things have thermalized or not, even qualitatively, but you can do it even for other initial conditions. We just put it on a lattice and put, odd and even K vectors to be +1 and 0. As a comparison, the red line is what a thermal, for example, distribution would look like. So you can see that we are far away from any thermal distribution to start with. And then we couple the system, use our equations, and try to find this object, which is the field correlator at time t, which you can roughly think of as 1 plus 2 times occupation number of the mode divided by omega k, where omega k is the phonon dispersion. Now, if we look at a k, which is 0.4 pi over a, it's kind of large, you see that it decays to a value. And the dashed line is what the thermal value is supposed to be. So if the momentum is large enough, the mode actually thermalizes. If you are at a low value of momentum, this is the thermal value, and the thing is basically oscillating around a value which is nowhere near the thermal value. So the low momentum long wavelength modes fail to thermalize. And you can get all of this in one shot by looking at the deviation of the long, so we do our averaging somewhere here over some long time to get one number. And then we look at the deviation of this correlator from the thermal value. And you see at large values of Ka, it's 0, and then it starts rising as the modes fail to thermalize. Now, why is this? So if you open up any textbook and look at the particle hole density of states of 1D fermions, you will see that at low K, there is an upper limit and a lower limit between which the density of states is finite. And so what happens is when you look at it at low K, the upper limit and lower limit is VFQ in both cases, plus minus order Q square. And unless your phonon velocity is very much fine-tuned to be exactly at VF, your phonons do not see any bath. And then it's not surprising that those phonons do not thermalize. So this is kind of expected. Once you go in here, you start thermalizing and see that you'll end up. Now, even here, if you do the calculations carefully, go to order by order in diagrams, you will find that in order kappa to the power 8, which kappa is system bath coupling, there is a term which will give you some slow relaxation to thermal thing even for this. So it's likely to be a pre-thermal state, which will finally very slowly decay into a thermal distribution. Now, I was doing this calculation at, if you see somewhere around 0.02 of the electron bath temperature or the fermion bath temperature. And now I'm going to very high temperatures. This is almost, 0.2 of the bath bandwidth. So everything is, all these energy momentum constraints are resolved. If you look at the density of states, they're there everywhere. So all the modes are seeing a bath, no problem here. But if you look at the deviation of the correlator at long wavelength, low momenta, you still see that they do not thermalize. So the question that we asked was, what is happening here? Why does it not thermalize at high temperature? Low temperature, it's kind of easy to see why they would not. what is happening here? Okay, so this is the picture. You are seeing the bath, but then we looked at the phonon spectral function at long times. You can Fourier transform the correlator and get the phonon spectral function. And when you see the phonon spectral function, you see two things. So this peak, broadened peak, is the original phonon dispersion, now broadened by the bath. But then you see a very sharp feature, which is kind of at a higher energy. And this is part of the dressed phonon spectral function. This is, of course, not there in the original phonon modes at all. This is coming because the phonon is getting dressed by the bath. Okay. And as you disperse, this also disperses, and you see that the spectral weight kind of decreases as you go to larger and larger momentum. So this is something that we have been calling a polarinon in essentially trying to make connection with polaritons, where you have excitons which are dressed by light fields and so on and so on. Okay, so what is happening here? What is happening is, in 1D, if you look at the bath spectral function, there is a 1 over square root omega divergence near the edge of the bath. Okay, and once that happens, you can almost say that almost all of the density of states is kind of at the bath edge, one way to think about it. Then you just have a two-mode theory, the bath edge, band edge, and the phonon. And then you're basically getting some bonding, anti-bonding orbitals. That's just a way of talking about it. In which case, these modes will go above the bath band edge. Once they're above the bath band edge, there's no spectral weight. They can't talk to, they can't exchange energy with the bath. And essentially, they become undamped modes, which lead to no absence of thermalization in this case. Okay, one way to see this is if you do, for example, Kramer's Kronig, you will see that you will force a pole just outside in the phonon-Green's function, you will force a pole just outside the bath band edge and so on and so forth. Okay, so that's kind of how we, that was interesting. We didn't expect this when we started with. And that's probably what I want to say. I have one more slide about the details of this, which I will skip for now. Let's go to the quench dynamics of bosons with dipole symmetry. Okay, so this is a recent paper, which is just on the archive, maybe about a month ago or half a month ago. So what are we trying to look at? We are trying to look at things, systems where the dipole moment is conserved. And for example, there are all these tilted Bose or Fermi-Hubbard models. There are even experiments with cold atoms, where the idea is that if the dipole moment is conserved, the charge cannot move, because if you move the charge, you change the dipole moment. But charges, one can move in, let's say, plus x direction, other can move in minus x direction while keeping the dipole moment fixed. So you end up with having correlated hopping. This has also been shown in a bunch of papers to be related to Hilbert space fragmentation and non-ergodic dynamics, some of which we have seen in this conference being talked about. We are not going to talk about that. We are going to talk about something simpler. There is also the connection to Frackton phases, which are phases which has some elementary excitations with restricted mobility. But this requires adding tensorial gauge fields plus other stuff here. And again, these are very unique things where you see a lot of non-ergodic behavior, large ground state degeneracy, and so on. So we are going to look at something simple. We are going to look at what correlations functions do in this system under non-equilibrium dynamics. Okay. So what is the model that I want to look at? So this is the standard phase symmetry, U1 symmetry, which leads to conserved charge. And I should have a model where the field phi should be, if it transforms to phi e to the power I d dot x, okay? So it's a phase which is linear in x, then the action should be invariant, and this is called the dipole symmetry. It's kind of in between global and gauge because it has some x dependence, but it's not arbitrary x dependence. And this would lead to conserved dipole moment. Now, this was written down by Pretko in 2018. He wrote down actually 2 or 3 different versions of actions which satisfy this. Okay, so you have charged bosonic fields, and they are this is the quadratic part of the action, and you immediately see one thing, that there's no grad square term, there's no kinetic energy. Single particles cannot move, so there's no kinetic energy term for the quadratic piece. If you go further, you will see that you can add terms where interactions have gradient terms in very specific ways. And so essentially any kinetic energy is nonlinear, and so it's ended up being a strongly interacting theory and so on and so forth. So this was a model that was written by Pretko, and we took this model. And okay, so in principle, you could write down a del T square or a I del T, and the model with I del T was studied by Jensen and Raz in 2205, in 2000. So what do we do with this? So we go to large n limit. We enhance, just put n flavors of this, because that allows us to do some large n theory, analytic approximations, and we scale the couplings appropriately by 1 over n and so on. Okay. So, and then this, if you Fourier transform, looks like we complicated k-dependent interactions. You do one more thing, if I can get to this. You regularize this on a cubic lattice. This is in continuum. You would have issues with divergences, so you regularize this on a cubic lattice. And in large n limit, essentially you end up getting some sort of a mean field theory where you will basically just get a quadratic theory, where the Green's function is dressed by some self energy and so on. You can walk through this, all of that. What is important is you will get an effective theory where now you will have a del T square plus omega k square. So omega k you can think of as a effective mean field dispersion. And omega k you can show has two parts. One is m squared, which is just the gap. And one is kappa, which is the curvature proportional to epsilon k. And if my kappa is finite, that breaks my dipole symmetry, because anytime I have a finite kappa, I have a finite dispersion, single particles can move, dipole symmetry will be broken in that state. Of course, I can also have the usual condensate, which breaks the, in this case, UN symmetry down to UN minus 1. So what are the possible phases we can get in this theory? You'll see that if you are gapped, UN is conserved. You can either break dipole or you can have dipole symmetry conserved. If you are already broken, if you are in a condensed phase, then the dipole symmetry has to be necessarily broken because you have Goldstone modes. And so it's not possible to have a dipole symmetry conserved while the UN symmetry or UN symmetry is broken. So these are the three kind of phases that you can expect. You write down a bunch of equations. Let's not go through them. You write down what you see after doing those saddle point equations. Only thing you want to take from this is that when I solve, I have multiple solutions, okay? Which is indicative that something like a first order transition is somewhere around the, I have to now choose which one has the lowest free energy and so on. When I do that, I end up with this diagram, okay? So I get two phases. This is m naught squared, the bare mass. I get two phases. One where m square is finite, okay? Kappa is 0, sigma square is 0. So both charge and dipole symmetry are intact, okay? And the other where the gap has gone to 0, I have a condensate, and I also have a curvature or a finite dispersion. So basically, this is where charge and dipole symmetry are both broken, and between them, I have a direct first order transition. That's what comes out of doing a large N theory of this. And you can do it for finite temperatures. Up to the points we went, it seemed like the first order persisted, okay? So remember that we could have gotten a state where m square was finite and kappa was finite, like where only the dipole was broken, but it doesn't occur, at least in this phase diagram. Okay, so what happens, our goal, of course, was to actually look at quench dynamics, okay? And then we use our formalism, etc., to write down those equations. And what that does is effectively you get a time-dependent mass. in terms of how you write down the equation of motion for the Green's function. You get a time-dependent mass or a gap, and you get a time-dependent curvature. Forget about the equations, they're nasty looking. There you can write down some equations for them because in terms of self-consistent equations. Only thing you care about is they involve this object called the Keldysh-Green's function, which is not this guy, okay? In the sense they actually know about distribution functions and so on. So the last thing that you need to do is you need to be able to write this Keldysh-Green's function in terms of the GR and etc. This is the retarded Green's function, etc. And this is where our formalism, etc. comes in and gives you a set of closed equations which you can now solve. I'm not going into the details, but this is what happens. Now, here are the results. Okay, so what are we doing? We are starting from m0 square initial at -18. We are deep in the condensed phase. We are starting from the ground state of the system. And then we are suddenly quenching the m0 square initial to the m0 square final. Okay, so when we quench it to a final value of, let's say, -11.5, you see that everything goes to a steady state. This is the dynamics after the quench. Kappa is finite, sigma square is finite, m square remains 0. So I'm basically in the condensed phase. Okay, in the steady state, I have a condensate, I have a dispersion, and I have no gap. Okay. What is more interesting is if I go to somewhere around -10.5, okay, my condensate is still now has gone to 0, okay, but you can see that the gap has become finite, and once the condensate has gone to 0, the gap will become finite, and you can see it from this case where m square is actually 1. But you see the kappa has a very large steady state value. So I have a gap, but then I have a dispersion above that gap, which means my dipole symmetry is now broken, although I have no condensate in my system. So this is not a state I saw in my equilibrium phase diagram. It appears only when I go to non-equilibrium, quench, and look at steady state after that quench. If I go further down, m0 square final of -9.5, and again, there's a break because I'm now looking at 980 to 1000 here. You see that my kappa m square has now become finite, okay, very large, but it's also oscillating, some quasi-stationary type of state. Sigma square has essentially gone to 0 even here. And kappa is doing something funny. It's oscillating, but it's also touching 0 at various points. Okay, so definitely your charge has U1 has been restored. Dipole symmetry depends on what you, if you are going to take the lower limit of kappa that it touches 0, it does, but because the whole thing is oscillating, it's a bit of a, depends on what you are going to talk about. But this is what happens to the steady state dynamics. So what we can do is we can take the dynamics here, let's say 500 to 1000, or even, and we can average the values, time average values, and then we can look at the time average values now as a function of how far I quench. Okay, so that's what we're going to look at. So here is the data. This is as a function of the final quenched mass. You see, this is kappa, and this is sigma square. Here I was going to a condensed phase. Somewhere around 11, the sigma square just went to 0 and remained 0. Kappa, however, remained finite very much. The mass started growing. So this, now the gray region is a kind of a phase where your dipole symmetry is clearly broken, kappa is finite, but your condensate is not there, okay? And then beyond this point, and you see there's a sudden drop at this point. If I look at kappa, it drops. If I look at m square, it jumps and so on. So that's why we have put the boundary there. You could have asked me that, oh, is this exactly 0? Why don't you put the boundary slightly later? And our point is, we see a very sharp jump, so something non-analytic happening there. So that's why we put the boundary of this phase in that. But this part is essentially something that is not there even at a finite temp. So it's not like I've just put in some quench and I've gone to some finite temperature phase. With the energies that we have dumped, this phase is not there in the finite temperature phase diagram either. Okay, so it's something that you only get when you quench the system in this case. Okay, and again, this, as I said, is a large N calculation. So you can ask what would happen if I add 1/n corrections and so on. Most likely things will go to a thermal state, most likely. I don't know, we haven't done that calculation for us to say it completely sure. So one thing we wanted to look at was, okay, we were doing the quench dynamics. What happens if I drive it slowly, like I ramp, okay, instead of just instantaneously quenching it? And so what we did is we changed the m0 square from initial to final value with a tan hyperbolic profile, which has a scale tau. So tau 0 is instantaneous quench, tau going to infinity is adiabatic ramp. And we wanted to see as a function of tau, what is happening to this three kind of steady state phases that we were getting. Here is the map. So, okay, what are we plotting? We are always starting deep in the condensed phase. So my initial m0 square is -18 in all of this. This is the final m0 square that I've go to in this. And this is the tau, okay? Now, when tau is small, you see this gray region. So there is a difference between, so this gray region is where we get this other phase where the dipole is broken, but the U1 is conserved, okay? And you see, as I increase tau, I go closer and closer to a adiabatic limit. This region essentially goes away. And after some point, there's just a direct first order phase transition, again, from a condensed phase to a phase where both symmetries are restored now in this case. Okay, so we get back that in the adiabatic limit, we just kind of get back the thermal phases that occur in thermal equilibrium. Okay, so this is what I wanted to talk to you about. There is a little bit of more, I guess. Yeah, I'm understanding. Yeah. So what we can do is we can also look at the quench dynamics now starting from the normal phase. I mean, if you have first order transition, you would supposed to get a lot of hysteresis and so on. So we wanted to now quench from the normal phase, ground state, and then see what happens. Now, in this case, because you are going to often go into a parameter regime where you're going to break a symmetry, you need to put in a seed. Otherwise, you will just not see anything. Okay. So what we would do is we would put in a SID value of sigma, even though we are starting here, which is 10 to the -6 or something, very small. And we can ask whether it grows or whether it shrinks or what happens to the system. That's how you look at the quench dynamics from the normal phase. Okay, so this is, again, initial mass m0 square is -4. Again, what you see is this thing. So the red dots are sigma square. And if you look at the inset, because everything is plotted on the same scale, you will see that there's a particular point where it actually jumps and starts becoming finite. Okay. The same point, kappa also starts becoming finite. Kappa has been 0 here and then jumps. Okay. And this is m square, which comes down, and this huge error bars are essentially how much is the oscillation, top and bottom of the oscillations. These are not, there's nothing root mean square or anything like that. It's just we are just giving you the m square is actually oscillating. This is the average value, and this is the top and the bottom. Okay, in this case, the intermediate phase does not show up. You just go from here to there, and you either see kappa 0, or whenever you see kappa finite, you also see sigma squared to be finite. Okay, so that's pretty much it's an interesting puzzle. We don't understand everything here, but sort of interesting puzzling things that we have been finding. So if you have any ideas about what is going on or how one can best think about these things, it would be very useful. So let me just thank my collaborators. This is Mursalin Islam, who is just graduating, and he's, I think, going to Max Planck, Dresden. as a postdoc. And of course, Krishnendu is here in the audience. So let me just summarize. I talked a little bit about, I didn't give you the details of this, that we have been trying to extend the Keldysh field theory for dynamics from different initial conditions. I talked about phonons coupled to fermionic baths, and both at low and high temperature, long wavelength modes do not thermalize, but for different reasons. And then we talked about interacting scalar fields with dipole symmetry. This is a closed system dynamics. And in the equilibrium, both symmetries are broken at the same time through a first order transition, whereas there's a new phase with a broken dipole, but conserved U1 symmetry seen in steady states up to the quench. I'll stop here and take any questions.
Thank you, Rajdeep. Questions?
Hi, just one question about the first part of the talk. So
yeah.
Suppose I want a minimal fermionic bath. Today I want to design a minimal fermionic bath that can thermalize the phonons.
Mm-hmm.
What do I do? Is it not possible, or is there a way to make some small...
You should take care of the diverging density of states somehow. See, if, for example, what we could do, you could ask, okay, so this is, yeah. So you see this 1/√square root divergence was giving you all these poles. For example, you can ask, does this happen in 2D? If I did a 2D, and the answer is no, because in the 2D, this is actually a weaker logarithmic singularity, and it does not, when you do a Kramers-Kronig, that does not give you these extra modes. So this very strong 1/√square root singularity is important to give it to you in the high T limit, okay? So one way would be to get rid of that, maybe add disorder or something that smoothens that, strong 1/√square root singularity. The one for the low T, I think you will find it very hard to change, other than the fact that there's some higher order system bath coupling which will eventually thermalize. Because this is very hard to change, right? And it has to be so fine-tuned that your phonon velocity has to be Fermi velocity, which I actually don't know of any material where it happens. So in fact, if you look at standard and whatever, at least solid state systems like nanowires and so on, the phonon velocity is about 10 times lower than the Fermi velocity. I mean, the best case scenario you will get, okay? So this is hard to get rid of. But this is also actually known, I think in 90s, I think Matthew Fisher and others had worked about not what the phonons would do, but what electrons would do in such a case. And there is some answer known from there that actually I think your rates would be of the order of T⁸ or T⁸, some very high power of temperature. So you will thermalize, but very, very slowly. That's this kappa to the power 8 term. But otherwise, this part is hard to get rid of.
Other questions? Okay, if there are no questions, let's thank Rajdeep once more.